Welcome back to linear algebra. In this video, we're going to be taking a look at the idea of linear transformations. This is the point where we can start transitioning this course from a course that's based predominantly on computation to one that's based predominantly on the idea of abstraction. The clipping on my camera is particularly silly today, so let's just dive right in. Let me get my head out of the way. And we'll start with some vocabulary that you should be very familiar with already. A function. And to define a function, we're going to denote the name of the function f, put a colon, and then a notation here, a arrow b. And we read this as f from a to b. And a function is a rule which assigns each element in set A to exactly one element in set B. We call A the domain of the function and B the codomain, which is probably not the word you were expecting to see there. The idea of a codomain actually is a simplification on functions compared to the range idea that you probably thought you would see. The range or image of f which we denote as f of a, is the subset of b which f actually can reach. So compare and contrast. When you've dealt with functions in the past, you've dealt almost exclusively with real valued functions of one real variable. If you've taken Calc 3, you've talked about vector valued functions and functions of a vector variable. But for the most part, real valued functions of one real variable. And for any real function of one real variable, under this definition, we call the domain all real numbers, and we call the codomain all real numbers. It's frankly kind of boring. And that's why you don't talk about the codomain much when you're exploring the algebra of functions. The range is the part of the codomain that we actually get to. So if you want to analyze functions in the sense of finding the inverse of a function, in the sense of determining whether an inverse exists, if you want to analyze functions in terms of determining whether a function is increasing or decreasing or anything like that, understanding the range of the function is important. In this course, we're going to be looking at functions more abstractly. We're going to be looking at functions that go in a number of different places. And for that reason, the codomain is going to be important because it tells you at a glance what the function is spitting out. For right now, this semester, or this video, we're going to be looking at transformations. A transformation is a function which runs between vector spaces. For right now, the only vector spaces we have are the Euclidean vector spaces, Rn, and that's what we're going to be using today. Coming up soon, we're going to look at ways of describing other constructions as vector spaces. And when we get to do that, we will have more generalization going on here. But a transformation, and I'll use capital T to denote my transformation, might go from one vector space, Rm, to a different vector space, Rn. So because we are generalizing functions, thinking about the range is a couple of steps further along than where we need to be right now. The first question we want to ask, in this particular transformation, we take in m-dimensional vectors and we spit out n-dimensional vectors. Understanding the dimension of the input and output vectors is already going to be a challenge for vector transformations. So that's why codomain becomes an important idea and something we have to think about when we get to the level of this course. Right? We've nearly gotten to our subject for today's lesson. We now know what a transformation is. It's a fancy way of saying function. I will mention that we will sometimes use the term Euclidean transformation to talk specifically about transformations between Rm and Rn. But as the title of this video suggests, what we really care about is a linear transformation. A linear transformation is, of course, a transformation. And I'm going to define this very generally between vector space A and vector space B. For today, we're only going to be looking at Rm to Rn, but the idea of a linear transformation will work for other vector spaces once we get there. And to make a transformation linear, we want to take any two vectors in the domain, we'll call them vector u and vector v, and we want to take any two real numbers, we'll assume these guys are constants, a and b. And the rule for a linear transformation says that if we take the transformation of a times u plus b times v, we will get a times the transformation of u plus b times the transformation of v. This is, for the purposes of linear algebra, what we mean when we say linear. You might remember we talked previously about a linear combination, AU plus BV. This is why linear combinations are so important, because they allow us to create linear transformations. Thinking outside of the space of vectors, as it turns out, something we'll get to a little bit later on, functions can actually be considered as vectors using something like the Maclaurin and Taylor polynomials that you learn about in Calc 2. You can turn functions into polynomials, and you can turn polynomials into vectors, which is very interesting here because you might remember a rule from calculus that says that the derivative of a times f of x plus b times g of x is a times the derivative of f of x plus b times the derivative of g of x. Likewise, the integral of a times f of x plus b times g of x dx is a times the integral of f of x plus b times the integral of g of x. The derivative and integral from calculus are the canonical example of a linear transformation. They are the most powerful ones that you've run across up until this point. Although it'll be a while before we get to the point of calling these functions f and g actually vectors, we'll worry about that in the future. Thinking about Euclidean vectors gives us a couple of really powerful theorems. These two theorems make it really easy to define linear transformations on Euclidean vectors. Our theorem claims that a linear transformation between Rm and Rn is defined completely by its action on the basis vectors E1, E2, up through to Em. Remember, E1 is the vector 1, 0, bunch of zeros. E2 is the vector that starts 0, 1, 0, bunch of zeros. Em is the vector that has a whole bunch of zeros and then a 1 at the end. So in general, Ek has a 1 in the kth row and zeros everywhere else. You might remember from the video on the Euclidean vector spaces right. I don't actually need that definition spelled out that way. Let's consider a vector in Rm. Oh, my words and my writing are not matching up today. I apologize. To be in Rm, that means that we can write V as some V1, V2, all the way through to Vm. And as we saw in our rules for basis vectors, we can expand this out and multiply each of those components by the corresponding basis vector. where each of these VKs is just a real scalar. So we take our vector, we list out its components, and we expand out with the basis vectors to write our vector in unit vector form. And what we have is a linear combination of a bunch of vectors. So if we want to evaluate our transformation T on our vector V, well, by substitution, that's T of the linear combination V1E1 plus V2E2 plus all the way down to VMEM. And since T is linear, we can split this up. Linear transformations split up over addition, and you can factor out scalars. So this is V1 times T of E1 plus V2 times T of E2 plus all the way down to VM times T of EM. And that's our proof. Because look at what we have here. In order to evaluate our transformation on this vector, all we need to do is figure out the transformation on each of the unit vectors, each of the basis vectors, multiply by the relevant coefficient and add them all together. Once again, I know we're talking about Euclidean vectors, not functions here, but I want you to think back to the derivative from Calc 1. When you take the derivative of a polynomial, this is exactly what you do. To take the derivative of the polynomial 3x squared plus 2x plus 7, you split that up and write it as 3 times the derivative of x squared plus 2 times the derivative of x plus 7 times the derivative of 1. The derivative of x squared is known. The derivative of x is known. And the derivative of 1 is known. And by knowing just that, we evaluate. The power rule for differentiation is a rule that says if you know, well, I guess the rule for differentiating polynomials says if you know the power rule for each power, you can split the derivative up into just using the power rule for each of those pieces and calculate that. And that's what this theorem is trying to tell us. If we know what is happening to each of the pieces, when we combine all the pieces to make something nastier, we can just split it back up and use those facts in order to calculate. So consider this linear transformation. This maps from the two-dimensional Euclidean vectors to the three-dimensional Euclidean vectors. The basis vectors for R2, the unit vectors, are 1, 0, and 0, 1. And I've established that this is, I forgot to actually put the words in. I've established that this is a linear transformation, and I've announced how the linear transformation works for each vector in the basis. So if I want to evaluate t of 3, -2, well, I can stretch that out and write 3, -2 as 3 times 1, 0, and -2 times 0, 1. Use the fact that t is linear to rewrite this as 3 times t of 1, 0, minus 2 times t of 0, 1, and use what was given to us in the problem. T of 1, 0 is 1, 0, 1. T of 0, 1 is 0, 1, -1. And now it's just some arithmetic on vectors. I get that the result here is 3, -2, 5. Just by knowing how the transformation works on the basis vectors, we can calculate the value of the transformation at any given point. Now, for this particular example, between R2 and R3, the vectors are fairly compact and easy to work with, and we're dealing with a two-dimensional vector space, so we don't have a lot of vectors to list out. Imagine, instead of looking at just this two-dimensional vector space, imagine we had a transformation going between R7 and R13, from a 7-dimensional vector space to a 13-dimensional vector space. In R7, there are 7 basis vectors. So we need to take the transformation of all 7 of those basis vectors and explain what 13-dimensional vector comes out of them. It would still work, but it would really be messy to write it out. So to save us some work there, we have another incredibly powerful theorem. For any linear transformation between Rm and Rn, there is an m by n matrix we'll call matrix A, such that T of V can be calculated as A times V. Now that is powerful. We don't need to know explicitly how the transformation works on every vector. We can compact it all, and represent that as a matrix. Of course, that's actually still the same thing. We create this matrix by simply setting the columns of the matrix as the value of the transformation on those basis vectors. And by compacting it like that, it gives us everything we need. So for the sake of not making too much of a mess, I'm not going to prove this theorem, but let's take a look at that same example we were just looking at before. We had the matrix, or the transformation, so that T of 1, 0 mapped to 1, 0, 1, and T of 0, 1 mapped to 0, 1, negative 1. To create the matrix transformation, we take a matrix and each column of the matrix will have the entry of the basis vector. So the first basis vector is 1, 0. It spits out 1, 0, 1. There's my first column. The second basis vector, 0, 1, spits out 0, 1, negative 1. That's my second column. And watch what happens if I take matrix A and I multiply it times the vector we were interested in earlier, 3, negative 2. Well, I take 1, 0, 1, 0, 1, negative 1, and I multiply times 3, 2. Remember the rules for matrix multiplication? You take row, dot with column. So 1, 0, dot 3, 2 is 1 times 3 plus 0 times 2, which is 3. 0, 1 dot with 3, 2 is 0 times 3 plus 1 times 2, which is 2. And then I have 1 times 3. I'm sorry, I lost a negative when I copied this down. 0 times 3 plus 1 times negative 2 is negative 2. And then 1 times 3 and negative 1 times negative 2 is 5. So we get the same result that we got before, a little bit faster. Any matrix can be represented using a transformation, or any transformation can be represented using a matrix. I said that completely backwards. So as a geometric example, let's go back to the two-dimensional vector space, R2. We'll just transfer from R2 to R2. And I want to take a transformation that rotates by theta. So if I have any vector in the Euclidean plane, I'm going to take that vector, take angle theta, keep the magnitude the same. I know my drawing is not making that obvious, but we keep the magnitude the same, and we just turn the vector a little bit. This is a very useful calculation in a lot of computer graphics applications. It's a useful calculation in an awful lot of applications, but computer graphics is one that I think is kind of a nail on the head kind of thing. If you are trying to construct a virtual model of some scenario and you want to rotate the camera, well, everything in the scenario is represented as a vector. And if we can just perform a quick calculation on each of these vectors, we'll get what the new picture looks like and everything will work very nicely. So what does it look like to take the transformation on E1, the vector 0, 0? Well, with a rotation of theta, that will take me from the point 1, 0 to the point, remembering trigonometry, this is going to have x component of cosine theta, y component of sine theta. In general, r cosine theta and r sine theta, but I'm dealing with a unit vector, so r is 1. And likewise, if I start with the unit vector in the y direction, rotating by theta will take me somewhere kind of hereabouts. All right. That angle is not in standard position, so we do have to be a little bit careful. In this particular case, x is the opposite side of the triangle, if I fill in the rest of that to make it a right triangle. So the x here is going to be, it looks like negative of sine theta. Negative because we rotated to the left and we ended up on the negative x-axis. And y will be the adjacent side, cosine theta. So my transform of 1, 0 is cosine theta, sine theta. And my transform of 0, 1 is negative sine theta, cosine theta. Putting that together means that I can represent this transform using the matrix. The first column is this transformation, cosine theta, sine theta. The second column is that transformation, negative sine theta, cosine theta. In our textbook, if you follow along, you'll notice that they go through a couple of other geometric transformations. This one is the most complicated. Having seen this, you should be able to work through on your own, but it works through it in the textbook, what it would look like to create a transformation for reflection about the x-axis or the y-axis. Another really interesting one is the projections. If you want to take the magnitude of a vector and just kind of push it down, magnitude of a 3-dimensional vector, but flattened into the 2-dimensional plane, or a 2-dimensional vector and flattened onto the x-axis or onto the y-axis. There's some really simple to use transformations for that. But with that, I'm going to wrap up on this video. Thank you as always for joining me, and I'll see you next time.